we're almost quorate, if that's the word. Thanks for feeding back to the third year teaching review meeting. Your reps have made some responses. Main response was that you wanted more clarity about what will be examinable and not examinable. I'll send an email around that so everyone gets it, but I will try to indicate the material through the revision sheets. You know, there's like these 5 summary sheets, 6 summary sheets for each section. That should give you an indication of what to expect in the examinations. The examinations, as I said before, will be broadly similar to the previous years. Okay. So, everyone have any idea who this is? Some old dead white guy in the modern parlance, and presumably a physicist of some kind. He's got some kind of instrument on the right here. I apologise that the replication's not that great. So this is Oliver Lodge. Anyone heard of Oliver Lodge? The physics building at Liverpool is called the Oliver Lodge Laboratory, so presumably he's a person of some repute historically. He was one of the very early pioneers in transmitting and receiving electromagnetic radiation, and therefore also one of the pioneers in particle accelerator science, amongst other things. But curiously, as we shall see a little bit later, he's probably the only professor of physics who's also been the head of the Parapsychological Society. So as well as being a physicist, he was also into psychical phenomena. You should look up the story of his life to understand why. It's fascinating. Really interesting person. So a little bit wacky, and there's a story you might come back to on that later. So we've been talking about antennas, and I realise it's a little bit noisy, so just to recap, we were looking at the relationship. Actually, I'll keep him on there on the left. He's quite nice to see, isn't he? Okay. He's watching down on us, as he would probably believe, right? So we had the difference between the Hertzian dipole, which was imagined as being a short section of dipole observed from a great distance, and we saw that the radiation pattern, the average power that we received, this is the Poynting flux, right? So this is the power per unit area, varied as sine squared theta. Okay, where theta is the angle made between the direction of the oscillation of the charges and the direction of observation. That's our basic idea. Now, we're going to regard that as being isotropic enough. So when I say isotropic radiation, obviously isotropic means equal in all directions. This is isotropic enough when we're going to compare it with other situations. So you should remember that, right? So when we say that these are non-relativistically moving charges, that they give a quasi-isotropic pattern, where quasi-isotropic means varying as sine squared theta. So we appreciate that there is zero power above and below the acceleration direction, and maximum power to either side. Okay? Alright? And obviously there is no phi dependence. Okay? We don't know which way around that Hertzian dipole is. It has no preferred orientation. So we have a cylindrically symmetric situation. Now, last week we considered the half-wave antenna as an example of a more general idea, which is that when I observe at a certain angle, theta, with respect to the center of the antenna, I need to take account of the small phase shift that occurs between the current which is occurring further up the antenna. So this current in the antenna has the same form at any given moment as the current in the center. It goes up and down with it, okay, because it's a standing wave. It has a different magnitude that we must take into account, but it also has a small phase shift because of the difference between the distance from the center of the antenna and the distance where that piece of current element is. So that's what we were trying to get across. So that has a radiation pattern which is modified. Okay? And the phase shift gives us this term instead. So we shouldn't regard that as the sine squared going down to the bottom. This should be, roughly speaking, similar to the Hertzian dipole. And for example, if the antenna length drops to 0, we should have this term becoming like this term. So perhaps we ought to draw it to see what it looks like. So I draw the antenna pattern as follows. So this is XY plane. This is the plane. This is the plane perpendicular to the acceleration direction. This is Z, the direction of the acceleration. So we still have theta as we had before. Okay. So remember, we're plotting some observation distance r. This is our 1 over r squared behavior. Okay, and we have the angle theta. Okay. So remember, we showed that radiation pattern for the Hertzian dipole. I'm going to draw that in dotted lines, like so. Not very well drawn. The printed notes have this a little bit better. Okay. But I'm going to draw it by hand because I want to keep the next bit separate. So this is our Hertzian dipole. So this has the sine squared theta dependence. Okay. So it's interesting to ask, what is the dependence in terms of the power emission for our longer, realistic half-wave antenna? Remember that at any given angle theta, I would be able to draw a little line out here and I'd say this is the power, that length of that line. This is a standard polar plot. Okay? So if I draw the half-wave antenna, okay, and I normalize it so that at theta equals pi by 2, I choose to have equal powers, then I see this behavior. It is more directional. Right? So remember, I regarded the Hertzian dipole as isotropic enough, but my half-wave antenna, okay, my half-wave antenna gives me more power in the plane. So remember, we thought about Windsor Hill again, so an antenna sticking out the ground. I'm going to get, for a given amount of total power output, I'm going to get more power than if I thought of it simply as a Hertzian dipole, which of course is practically advantageous. Right? Doesn't look like a lot more there, but it is more, and that's important. So this suggests something. It says, can we do anything else? We've seen that that when we have a single antenna which is extended in length, we see a phase shift. So obviously, we can think of real practical antenna systems which are composed of many of these objects arranged appropriately to give the right kind of phase shift. So these are called antenna arrays. Now we're not going to look at those any further, but the basic idea is analogous to the situation of something like the diffraction grating. Okay? I will get constructive and destructive interference at certain angles depending upon the spacing and size of the antenna. So let's imagine now, this is X and this is Y. I imagine now a number of these antennas. So let's put one at the origin, that's maybe our original one, and I add some more, and I space them in some manner. So a simple spacing might be, say, lambda by 2. Okay? And in that situation, I will get even more interference, and I will get an even more directional pattern for the radiation. Okay. Now the rest is detail, you might say. That's the basic idea. Okay. Ooh. Slide it up. Sorry about that. I'll slide it up. Now what else might I do with a set of antennas? As well as having a particular spacing chosen, what other things might I choose to do? Imagine I've got current going up and down in each of those half-wave pieces. What else could I perhaps do to change the radiation pattern? No one likes shouting out. This one is the way. Last year everyone was shouting. That's quite funny. So here is my Hertzian dipole and my half-wave antenna. Okay, and if I have a set of them, I can enhance that interference to give me some kind of more directional output. But I can also do quite wacky things. Okay? I can quite dramatically modify where the radiation is going, not only by choosing the spacing of the antenna. So imagine I build a set of these antennas somewhere. I can also change the phase of the current fed to each of the antennas. So this is called a phased array. Okay, so a phased array, here this particular one, we have 6 antennae. They're spaced apart, about 50 meters apart, so we can imagine building one of these, can't we? Okay. And you introduce a phase shift of 90 degrees in the output of one antenna compared to its neighbour. Okay. And now, rather than having a radiation pattern which is pointing either up or down, I can make it point in one particular direction. So I can do radar with this as well. Okay? So this is a basic concept which is used extremely widely in telecommunications. Okay? And again, I'm not going to go into it in detail, but that's the basic idea of it. Okay. So hopefully that's rounded off section 2. So maybe a bit of a highlight, hopefully. Okay. It's the core of the course, I'm going to suggest. That may give you some idea about examinations. We should really talk about things which aren't vacuum. So what we've talked about? We've talked about plane waves, we've talked about energy conservation, we've talked about the nature of the coupling of the electromagnetic field to charges, and we've talked about the use of acceleration to generate radiation. That's our source term. The thing we haven't talked much about yet is what happens in interesting materials, things which aren't a vacuum. So we should probably move on and talk about radiation in matter. So let's do that. Okay, let's kick off. I think we're going at a reasonable rate, by the way. I think we're going to have lots of time for discussion a bit later on. I'm hoping that we can kind of skip through this at a fairly brisk rate. So again, like before, to begin with, this lecture will be mostly revision. Right? You'll see these stuff before. I'm going to go through that, and then we'll talk about the interesting stuff, and we'll get to some of the crucial bits, which is plasmas. Propagation of electromagnetic radiation in plasmas is really interesting. Okay. So I'm going to talk about Maxwell's equations in a medium. And of course, Oliver Lodge, he was very keen on... Sorry about that. Yeah. Oliver Lodge was a parapsychologist. He liked mediums, but that's not the same kind of medium. So this is a reminder. So what are the basic features of a material which has some kind of electric or magnetic properties? Well, the first thing that can happen is we can induce a polarization in the medium. And that polarization is proportional to the electric field, clearly. And we have a scaling, quantity epsilon 0, that's a unit scaling. The important thing is the material property, and the material property is this susceptibility, the electric susceptibility. So it's merely stating that the polarization is proportional to the electric field with some scaling value that depends on the material. That's the meaning of the equation. An equivalent statement is the magnetization, which is equal to 1 over mu naught. Okay? And then I have the magnetic susceptibility times the magnetic field which exists within the medium. Okay? But already, we note something which we must take account of, which is it's unlikely that the polarization response of material to an electric field will be truly linear with the strength of the electric field. Presumably it will saturate at some point. It will become non-linear. Okay? Also, how is the polarization being developed? It's being developed because of the motion of electrons which are attached to the atoms of the material, which are moving in response to the electric field. They cannot move infinitely quickly. And we're thinking about, high frequency electromagnetic radiation passing over materials. So we expect that there will be a frequency dependence of this susceptibility. So we expect, therefore, that the polarization will be some function of the electric field and some function of frequency. So we should be aware of that. And the same thing, of course, will be true of the magnetization. But as we shall see, most things are not magnetic. This is for completeness. Now we can conveniently define these relative permittivities in terms of the susceptibility. So this is just a rewriting of the same physics, but in a way which allows us to write down other equations more conveniently. And we can write down a relative permeability, so 1 over 1 plus the magnetic susceptibility. And when we do this, we can write and we can define and write the so-called displacement vectors. Okay. And this magnetic intensity, which should be a D, of course. And there, the susceptibilities have disappeared. That's the reasoning for having these definitions. And we can define the displacement vector in terms of the total electric field and the polarization. And similarly, we can define the magnetic intensity in terms of the magnetic field, take away the magnetization. And I would suggest that this one here, again, we're not going to see much of this one. Okay? This is really saying that if I apply a certain driving force to a material, okay, I get a magnetization, and the magnetic field is a combination of those two things. And of course, we can modify Maxwell's equations as you saw before, okay, where we define, instead of the total electric field, we define the displacement vector in terms of the free charges, in other words, without the polarization. We still have del dot B equals 0 as normal. Okay. Faraday's law remains the same. Del cross E equals minus dB by dt. God, handwriting's bad today. dB by dt. And then del cross H is similarly modified in the same way that the displacement vector is. Okay. And I can write it again in terms of these so-called free currents, which becomes convenient. Now, in just the same way that physically the polarization and the magnetization must be frequency and field dependent. Okay? Why are they frequency and field dependent? Because of the limited ability of the atoms to respond to the application of those fields. Therefore, the permittivities and permeabilities, you are, okay, must also similarly be functions of frequency in reality. Now obviously we're going to look at interesting simple cases, so I'll slide up and keep it still. We look at interesting simple cases. Now there's another property of a material which we must also take into account. We've so far thought about the polarization and magnetization due to the electric and magnetic fields. We'll also be talking about moving charges, which of course are currents. And we expect, of course, that a current should also be a function of frequency. Okay? Okay, so these are indicator equations, aren't they, that tell us how these things behave. Now, in a real material, let's just draw a picture of that. So here is some arbitrary electric field, okay, moving over a collection of atoms. So our picture is of, well, I mean, the atoms contain both positive things and negative things, don't they? Material matter contains both positive and negative things, which we're going to assume are overall neutral. And we'll also assume that somehow, for a given electric field, the motion of the positive things is less because they're heavier. We shall see that's extremely important in trying to understand plasmas. So we imagine in a solid material, the nuclei are somehow stuck together in some way, and they're not going to move around. And the electrons can. In a plasma, well, everything is free to move around to first order, but we'll see that for a given frequency or a given amplitude of electric field oscillation, the electrons are going to move more. They have the same charge and a lower mass, aren't they? So the electric field is basically, we're going to assume it only moves the electrons. That's going to describe 99% of what's going on, which is what physics is all about, isn't it? Okay. Now you'll see here that the response of the medium, in principle, not only depends on the instantaneous value of the electric field, it must also depend on where the electrons happen to be due to the electric field that was there at some earlier point in time. Okay? So we're going to kind of ignore that and assume a steady state response. But we should point out that the response of the medium does in principle depend not only on E, not only on the rate of change of E, which you can describe as some kind of instantaneous frequency omega, it must also depend on the history. So we shall be implicitly talking about a single electric field with a single frequency passing over the atoms, okay, such that we have an equilibrium situation being brought about. Because otherwise it's just too hard, isn't it? Okay. So how are we going to describe our response? We're going to look at plane waves, aren't we? Of course we're going to look at plane waves, because they're the easy ones. Okay? So we're going to think about plane waves. So the plane waves have a given omega, right? And we're going to assume to begin with that our material, okay, so it's given omega passing over atoms. And our atoms are going to be responding linearly. Okay, so it's a linear medium. And the other thing we haven't said is we realise that in real materials there could be some dependence of the material's response depending on which way the electric, that's this plane wave, is traversing the material and what its polarisation is. Okay, which is almost the same thing, isn't it? I could imagine that my atoms are somehow aligned, crystalline alignment, molecular alignment, things like that. So I must also assume that the medium itself is isotropic. It doesn't care which way the plane wave is passing over it. So that's our simplest case, and it will suffice for most of what we're doing. And because it is a plane wave that we're assuming, this means that we have implicitly assumed that there's an equilibrium being formed, so therefore the history of the electric field is not important. Okay. And then we just do what we normally do. We say, let's define the electric field in some manner. We'll define it in a manner which is simple. So I assume it has only one component. And let's assume a magnetic field that may also be part of that wave, which presumably has a magnetic field pointing transversely to that. And in the way of defining it, this must mean that the electric field, if it's a plane wave, is moving in the z direction, omega t minus k, kz, okay? And the magnetic field By must also have some, this is a 0 and that's a 0, okay? And again, we've said for a plane wave, okay, for a plane wave, we have a common frequency and presumably a common wavelength. Now we're in a medium, we can couple those electric fields together. Sorry, they can couple the two fields together, the electric and the magnetic field. They're coupled via Faraday's law, aren't they? So we substitute into Faraday's law. Faraday's law, okay. Okay, but in the medium this time, so we need to take account of the medium properties. So when we substitute, we get an expression that looks like minus ik E0 e to I omega t minus kz. Okay, so just apply that cross product and show that you can do this. It's minus I omega B0 e to the I omega t minus kz. Okay. So obviously the i's can be cancelled. Obviously the variation can be cancelled. And hey presto, B0 over E0 equals k over omega as before. Now the fun happens when we substitute into Ampere's law. So now we substitute into Ampere's law, this result, this coupling between B0 and E0. Okay. We get the following expression. Let's write on a fresh piece of paper to give us some space. Fresh space. Because it's fairly lengthy. We get the following expression: I k B0 e to the I omega t minus kz. Okay. And so what we've written out here, this is Ampere's law. So we've got the left-hand term, so we substituted the magnetic field on the left, and then we've got this term on the right, which is, we've got the two parts, haven't we? We've got the variation of the electric field, and we've got the currents. Okay. So I get epsilon r, epsilon naught, mu r, mu naught. Okay, so we assume to begin with that we have all those material properties. And then we also have to substitute Ohm's law. Okay, so I should really put up here Ohm's law. Because we want to relate J to the electric field. Okay, so that's what we've done here. We've changed the current to the effect of the electric field on the charges in the material. So it must have the conductivity that appears. And I should put on the right there. Okay, let me write that up. Let me write that up a bit better. Let's do it one more time. I k B0 e to I omega t minus kz. Okay, equals I omega epsilon r, epsilon 0, mu r, mu 0. Okay, plus mu r, mu 0 sigma. Okay. And again, I'm imagining this electric field passing over E I omega t minus kz. Okay? And then what the first step I do is I take the Faraday's law result and I replace this bit here with k e0 over omega. And then of course I realise that everything is moving together in phase. So I get this result, which seems a bit opaque to start with, but it determines the properties of all these different materials that we're going to see. I omega mu r. Okay, so notice this, that when I cancel out the i's here, an I has to appear there, so it comes in as a minus I. Okay? So this, what does it mean? This is relating the wave number, and therefore the wavelength, of any plane wave passing over a material to the frequency with which that plane wave is oscillating. Okay? And we saw something before. We saw the simpler case, right, of a plane wave in space. In free space, we saw an expression that was like this, omega squared over c squared, right? So you can see if there's no conductivity, and there's no permeability and permittivity, in other words, it's just free space values, then we have this relationship between the wavelength and the frequency. Okay? So both of these will tell you that as you change the frequency here, the wavelength here changes, doesn't it? Because these material properties, you have some effect of the conductivity and the permittivity, which may also change. So this tells you that there is dispersion, right? So because there's dispersion, I have a different wavelength as a function of frequency. Over and above what I would guess just by having this free space situation. So these two things are both called dispersion relations, right? So a dispersion relation is a thing that for a given omega defines k, the wave number, and therefore the wavelength. Okay? It's most conveniently written in terms of k. So this is our case in a material that has permittivity, permeability, and a finite conductivity. And this is the situation in free space. It's obviously easy to check that. Okay. Now the most important thing to see here, there's a complex value that appears. Which indicates there should be some phase relationship between omega and k. Now also we can also remark that we can rewrite that dispersion relation in terms of the free space value, but I need to modify it for the particular material I'm in. So it has particular mu r epsilon r, but I still need to include this conductivity value. Now notice the conductivity value does not have any permittivity term in it. So go to the notes and just see that you can do that substitution and show yourself that that dispersion relation holds. Okay. Now there's a variety of ways that we can examine or sort of note the behaviour of this equation. The first thing is, we've seen straight away that if sigma is 0, then there's no complex part to this expression. Which means if sigma is 0, then k is real. Right? So we don't have to worry about the fact that this wave number has a non-real component to it. What does that mean? Because when sigma is not equal to 0, and there is some conductivity, k has a complex component. See, that's quite important. We'll see. We can rewrite this actually. We can say, let's write k, the wave number, in terms of some say free space part. Call that k0. And then we can write down the effect of the permittivity and the permeability as modifying the speed. So there must be like a speed part that appears. It must depend on epsilon r and mu r. Okay? So that's the situation if the conductivity was 0. Okay? You can see that would modify the wave number for a given frequency. We can rewrite that top part. We can write it like so. Okay? So this is a real value that modifies the speed of the wave, and this is an absorptive part, because as the wave propagates, as the wave propagates, the fact that k is complex tells me as z increases, I should have a real term that appears as a function of z, and therefore the magnitude of the electric field should fall. That's what the consequence of that I term is giving us. And we've written this down by saying that k0 is equal to omega over c. So you might call this the vacuum value for k, the vacuum wave number, which gives you the vacuum wavelength. That's one way we could write this. Okay? So we're going to use both of these concepts. Now another way we could write it, we could break apart the real and the imaginary parts. Okay? So we suggested that this presence of this complex value here, let's zoom that out real quick. Still see okay? Right, just want to keep a balance between seeing off the page and seeing the individual values in. So I'm suggesting that because we have this real conductivity, we get a complex value that appears in this dispersion relation, and therefore we expect to see some kind of absorption. Let's see that explicitly. We're going to rewrite k, we're going to write it as a real part and an imaginary part, and I'm going to write it down as minus k iki. So I've got a real part for k and an imaginary part of k, and obviously I can relate that to these terms here in some manner because there's a square root that has to be done at some point. But let's say that k has a real part and an imaginary part. We see that there must be absorption going on if there's a complex value for, if there's a value for ki. We write down the electric field in x. Well, clearly it's E0I omega t minus kz. And of course, our job with working out the dispersion relation is working what k is for that particular value of omega. I could break that apart now into E0 e to the I omega t. Okay, that bit's easy. That's just the fact that the electric field at any given position is varying with time. That's obviously happening, isn't it? Then I've got the spatial variation, which is e to the minus ikrz. So this would be the situation in a vacuum as well. And obviously this is telling me that as I change the value of z, I'm changing the phase of the wave, okay? The peaks, the peaks and troughs. It's telling me I have a wave, of course. And then, of course, I've got this e to the minus kiz. That's why I put that minus sign in the definition above. Because if ki is a positive value, it tells me that as z increases from some starting point, I should have a decay in the amplitude of ex. Okay, that's if. Okay, so it's decay if ki is positive. So ki itself is a real number; it's a positive value. And let's just check that ki really is 0. So ki is real and positive. Let's look at the signs of the things which determine it. So we've got our dispersion relation above. Okay, so let's just bring that back up again. There it is. Okay. So those are the terms that determine k for a given omega. Let's go back again. So we know that obviously the frequency is real positive. We know that permeabilities are real and positive, both μr and μ0. Okay. And we also know that conductivity is positive. We don't get a negative current for a positive voltage. Okay. And that means ki must be greater than 0. Okay. So if I have a positive conductivity, I have damping. Okay. So my definition above is the right way around, and everything is as you might expect. So what does that mean? It's slightly counterintuitive. So what we say is that a finite conductivity material, a little bit counterintuitive to start with, but it's true. A finite conductivity, sigma, means that a plane wave is absorbed. Okay? Plane wave is absorbed. And from the look of it, it looks like the larger the conductivity, the greater the rate at which the plane wave is absorbed as a function of distance. seems a bit weird, doesn't it? We'll have to look at that. Okay. So that's our general statement. So I'll just bring back that dispersion relation. So I'm going to keep looking at that. Okay. So we're going to look at three situations, two of which are basically the same. So it'll save us a bit of time. So there are three interesting situations. Well, I'll let you judge if you find it interesting. Hopefully you find this interesting. The first one, of course, is when sigma is equal to 0. So we call those dielectrics. Okay? So sigma is approximately 0. And in all practical dielectrics, here's our jump. So we did the general statement that has mu r's in them. But I'm just going to go mu r equals 1. Okay? And I remind you, once again, watch out in textbooks, watch out for people just dropping these mu r's, because they will do. And we will as well. Okay? And the opposite situation is that of a conductor, where sigma is not equal to 0. Okay? But I'm going to say it's large enough, in some way we're going to define, but finite. Okay? And then we have these other things called plasmas. And similarly, plasmas also have a conductivity which is not equal to 0. Okay? But it differs from a solid, obviously. It's a different state of matter, some people say. And of course, a plasma can be considered to be a gas of ions and electrons. So different to a solid, both the ions and the electrons can move under the action of an electric field. They can move freely because the material as a whole, both in large scale and smaller scale, remains electrically neutral. So there's no restoring force of the electrons in a plasma if they move, whereas it is a restoring force if the electrons in an atom are moved. Yeah? The electrons are attached, they can be brought back, whereas in a plasma the electrons are free, and in a conductor they're also effectively free. Right? The difference, of course, in the plasma is the ions can move under the action of an electric field, but we're saying because the electrons have a much lower mass, we can ignore the ions, and therefore we can treat conductors and plasmas as the same. So they have basically the same properties. So a metal, which is a common example of a conductor, as you know, has the same properties for the transmission of electromagnetic radiation as a plasma, maybe with different frequency scales, but conceptually it's much the same. And that's an important statement that we're going to look at later. Okay. So that's our definition. So we should now look at those two cases, or two or three cases. We should probably move on to dielectrics. I'll just stop for a moment, halfway through. Any questions so far? Do have a go at doing that Faraday and Ampere's law substitution for a plane electric wave, and see if you can show that dispersion relation. Okay. Waves in dielectrics. So our first case is dielectrics. So, dielectrics, mu r equals 1, approximately, close enough. Conductivity equals 0, close enough. And therefore we know that the phase velocity, the velocity that appears in our plane wave equation, v equals omega over k, which according to our dispersion relation has become 1 over mu r, mu naught, epsilon r, epsilon naught. Okay? And because mu r is 0, and because I can swallow up mu naught and epsilon naught, I see that it's equal to 1 over c root epsilon r. And I will clumsily in some of the notes swap between using epsilon r and epsilon. Okay, so if you see epsilon sometimes it means epsilon r. Usually it means epsilon r. Okay. Now, of course, the relationship of the velocity in a medium to the speed of light suggests straight away that because the refractive index is equal to c over v, it must be equal to the root of the permittivity. Okay. Now, that's not everything. So we said there's no absorption. Okay. But we do actually see absorption in dielectrics. So we should probably try to describe that. So that's our base statement about the nature of waves in dielectrics. I modify the velocity, but we also see other behaviour. So experimentally, we do observe some behaviour. We see, experimentally, as frequency is varied, okay, in other words, imagine different colours, as frequency in wavelength, okay, over some kind of range of interest that we often come across. We'll see what that means in a bit. We see that the refractive index is a function of frequency, okay? And that's of course because permittivity is a function of frequency. So I write down carefully that the refractive index of material varies its frequency. I can relate that to my dispersion relation like so. Okay, so for a given frequency, I can determine the wave number for that frequency, and that determines the refractive index, and obviously that is related to the permittivity, which also varies with frequency. Now we see something. We see in real materials the following generic behaviour. So I'm going to plot two things. The first thing I'm going to plot is as I increase frequency from some low value. So remember, imagine doing an experiment. You start at some finite value and you follow the refractive index as a function of frequency, and what you find is that it goes up, okay? And usually it goes up. In fact, at some higher frequencies it also goes up, okay? But there are some regions where it doesn't go up. So normal materials, or the normal frequency range, is that situation where the refractive index rises with frequency. But there are anomalous regions. I'm trying to draw those carefully. There's a peak, comes down. Okay, so there must be an anomalous region there to there. Okay. Anomalous. In some frequency range, where as the frequency goes up, the refractive index goes down. Okay, so normal. Omega goes up means that n goes up, and anomalous, omega goes up means that n goes down. Okay, and what you see experimentally as well is that if you were to take a beam of light and select one frequency from it, okay, that you get no absorption in the normal regions, but you do get some absorption in the anomalous region. So that's a generic statement. But in reality, there are actually many of these. There we go. And n, so if I were to look at the refractive index of a real material, a real dielectric, there actually turn out to be several regions of anomalous dispersion. So I'm just going to draw a dotted line to indicate there that they may be spread apart by, some distance which is large in comparison to the width with which I've drawn that anomalous region. So it's meant to be a cartoon, right? So presumably there is some kind of special frequency at which I get the maximum amount of absorption. So there's no prize for guessing what is the origin of that absorption. It must be some kind of transition. Okay? So as well as the electrons changing their behaviour and oscillating at by different amounts depending on the frequency, there also are regions where they will absorb. Okay? Now let's just, so there are several of these, okay, for any particular given material. We might imagine these happen in the visible spectrum and other parts of the spectrum, because we know that the energy levels of the electrons are anomalous dispersion. Because we know that the visible spectrum happens to coincide with typical energy levels of atoms. It's several eV. Okay. So in many materials, there will be this absorptive region in the infrared. Okay. These are our anomalous regions. Okay. Where do they occur? Anomalous. in some materials, we get these anomalous regions where we have absorption happening in the visible part of the spectrum. And this, of course, what gives rise to the phenomenon of colour. That's why our seats are green and shirts are fetching blue. And in most materials, again, because of that statement that we have these transitions of several EV, UV light is several EV, we imagine that most materials will have an anomalous region where I get absorption in the ultraviolet region. Okay. Now, I'll let you confirm for yourself what the frequencies are for these that go with these. Okay, so I'm giving you a clue. This is obviously visible, several EV. Okay, I'm going to write it down in another form. I want you to check with a calculator that what I'm saying is correct. For frequencies greater than about 10 to the 16 Hertz, which is above all of this, we get a kind of quasi-constant situation. Okay. We also observe that the refractive index of most materials, most dielectrics, is 1 in nearly all materials. That's another experimentally observed fact. Okay. Now, as we have seen from our discussion so far, and we'll probably wrap up at the end of this, that implies that if n equals 1, and it's a non-conducting material, we therefore expect that at very, very high frequency, we expect very little absorption. Okay. We've already said that we expect there to be absorption bands in the IR, the visible, and the UV, but at very large frequencies, which of course are X-ray wavelengths, which we're talking about tens of nanometers or shorter, for example, we expect no absorption, so this is one of the reasons why we expect X-rays to penetrate matter. Okay. And because the refractive index is 1 for virtually all materials, that means it makes little sense to construct an object which is going to try to focus these X-rays. Okay. So you can't make a lens for X-rays. Okay. Lenses work because the refractive index of the object is greater than 1 significantly, but it still allows little absorption. Okay. And similarly, gamma rays of even higher frequency, say f greater than 10 to the 19 Hertz, say. So we're going to start talking about MEVs there, aren't we? There's an appropriate unit to choose for each of these types of phenomena. Okay. Gamma rays also do not effectively refract through any dielectric, do not refract in any dielectric. We'll see later that gamma rays can be distinguished from X-rays for the purpose of what we're talking about, but in terms of refraction, they aren't. Okay. So our job for Monday is going to be to try to describe this behaviour using a simple model. So we're going to talk about the polarisation of the atoms, and remember that our key concepts here, our key concepts here were that in the dielectric, the electrons are attached to the atoms, and therefore we're going to expect there to be a restoring force, and there should be some kind of oscillator model that we can develop where we can include an absorptive term, some energy removal term, right? So like any other simple harmonic oscillator. So that's what we're going to go through in the next lecture.